and get much more accurate results. This session is going to be dedicated to solid edge simulation tips and tricks. Why is it important? Tips and tricks are kind of shortcuts into different options that might not be obvious or maybe overlooked or not so popular. But these little tips and tricks, they might improve your productivity drastically. And that's what we're going to take a look at today. First stop would be united body analysis. Let's face it, in simulation, setting up a study is quite a time-consuming task. So with this united body approach, you will be able to shortcut into your results in no time. Second stop would be mesh body analysis. This is very welcome addition to solid edge simulation in solid edge 2022 as more and more requests coming from the field for analysis of a mesh body. Because of 3D printing, now a very hot trend in the industry, people designing and people scanning different designs into STL files, and they bring those files into CAD, and they want to be able to analyze their designs before they go into production. So we're going to take a look at that capability. We're going to stop and look at meshing options. There are a couple tips that I'm sure you will like when it comes to dealing with far from perfect geometry. When there's situations when geometry is imported from outside of solid edge and there are some imperfections that prevent you from successfully meshing them right away, there is a couple tips that will help you overcome those challenges. And finally, we're going to take a look at how would you display internal stresses in the parts. Specifically, it's important for parts such as pins, bolts, any hardware. And customers ask me multiple times, how would you display internal stress in those parts? So we're going to take a look at that option. So with that, let's begin. In this example, we're going to take a look at how solid edge simulation can help you be more productive when it comes to thin wall parts, sheet metal designs. As you can see, this computer rack consists of sheet metal components. And the normal workflow would be to extract meat surfaces and create some connectors and solve the study. So let's see how it works here. We're going to go and extract meat surfaces. As you know, with solid edge, it's quite easy to do. We can do it even on assembly level. So we can extract meat surfaces from all these components. And of course, when we do that, solid edge simulation will know all about material and the thickness of the parts when we add them to the study. So let's go and hide all the components, and it only leaves us with the extracted surfaces. But instead of doing all this work, because you can imagine that when we add all these components to the study, we would have to go and manually create connectors for every member of the structure. So if I open this simulation tab on the side, you can see all these mid surfaces extracted. So instead, what I'm going to do, I'm going to use this Unite Body functionality available in Solid Edge. I can select all these components or extracted meat surfaces and combine them in one united body. It significantly reduces the time required to set up a study. So when I go and create new study, the only trick here is that you need to select mixed and general bodies type of mesh. Then you will be able to select this united body and use it as your geometry. And of course, it's all modifiable. So for instance, if by default system assigns materials as steel, we can always easily go and change back to aluminum. Or if a system allows thickness to be 1 millimeter, and I know that it's supposed to be 1.5, I can change the thickness for all components at once. But you might ask, what about unique thicknesses? No problem. We have this tool which allows us to override properties for specific components or surfaces, I should say. So I can go back and let's say change it to 3 millimeters for a couple components. All I have to do just surround all these faces and assign new property, override that property for the full component thickness. And by the way, this is override property is always changeable, so I can edit definition and go back and change material and thickness. This is a great productivity tool, allows you to quickly and efficiently set up your study. So let's go and define loads and constraints. This is quite a straightforward study. We can define it, say, about 200 pounds of force load. And as far as constraints, we're going to go and define fixed constraint on the bottom. Of course, we're holding structure, standing on floor. And that's pretty much it. We don't have to deal with all these connectors. We can just go mesh and solve in one single operation. And because it's a one single body now we're analyzing, the analysis will come in really quickly. And as you can see, we have results in no time at all. And it's very convenient, very user friendly. So let's animate this design in the post-processing window, and let's see how it behaves. I usually tell customers that's a good idea to take a look at exaggerated animation of results because it gives you a good idea, good indication what might be wrong with your study. And sure enough, when we look in closely, we can see that not every connector is in place because some of the walls, some of the elements are still protruding through other elements, as you can see here. No problem, because we can use connectors as well. Even though it's a single body, we can still use connectors to fix our design. As you can see right now, the stress is 55, around 55 megapascals. Let's go back to our design. Let's add some connectors. I'm going to choose edge connection, and there are a couple different ways you can connect edges. You can do glue connector or you can do rigid. The difference is if you pick glue, you'll connect edge to a face. If you need to connect two edges, edge to edge, you pick rigid. So in this case, we can do either manual selection quite easily. We can focus only on the specific edges that are required. Let's say a couple edges on that side and a couple edges on this side. Define the search distance, and then we're going to select faces that we're going to actually connect to. So this way we can precisely focus only on edges that need fixing. Or you can go and do it with a window quite easily and efficiently. We can create another connector. And this time I'm going to select set of edges here and on the top location. Very efficient, very user-friendly. Same way we're going to define search distance. And then we're going to select the faces we're going to connect to. And the same thing on the bottom. So in one single operation, we were able to connect many different faces and edges in one single operation. Very efficient, very user-friendly. I'm not going to bore you with the rest of it. I'm going to show the results. So as you can see, I added all the required connectors. So let's go and solve this study. Conveniently, we don't have to remesh. We don't have to redefine all the boundary conditions. Everything is in place, and all we have to do is just hit solve. And when system comes back, we'll see our results in no time. So now you can see that we are significantly lower on stress. So right now we're at 29. We're almost at the yield stress. So if we animate our structure this time, you can see that nothing gets protruded into adjacent components. Everything works as designed. And this is a little trick to look into animation and make sure that every member is doing its job. Another trick which would significantly improve your productivity and accuracy of the result would be to utilize this study to do a different type of analysis. So let's say right now what we've done, we created static study and we get linear static results. What about buckling? With structure like that, it's very important to check for buckling to make sure that it works within limits. So quite easily, I can select this study, drag and drop on a simulation, and it will create exact copy of that previous study. And then easily I can go and say modify study and switch to different type. Instead of linear static, I'm going to go with linear buckling. And system warns me that some constrained loads might not be appropriate, but I'm okay with that because I know they are. And again, all I have to do just hit solve. There is no actually work involved. You just copy the study, change the type, and hit solve. It takes in account all the boundary conditions, all the loads we set up prior to this, and in one single shot, we'll get results on buckling in addition to linear static simulation. And of course, the way buckling works, it delivers the value multiplier, eigenvalue. So if we go and take a look at all these eigenvalues, the lowest value is half. You can see 5.5 e minus 1. So it means 0.55 of original load. So what it means that with a 200 pounds load, it might start buckling at really half of that load, at 100 pounds of weight. And you can easily compare results and see what is the weak link in this particular structure. So we can take a look at the results of a previous analysis easily. And of course, under display options, we can take care all the options that required. So we look at stress, and we can always go back and look at our buckling results. So this is a great approach in analyzing this type of structure efficiently using united body approach, as well as ability to create copy and change the type of the study. Really helps with productivity and getting to results quickly. In the next example, we're going to take a look at ability to analyze mesh bodies. This is very important improvement in solid edge simulation because, as you know, generative design produces mesh bodies, and that will be very beneficial for potential customers to be able to analyze those bodies. Before solid edge 2022, we were able only color map those results to see where the stress is the strongest. But now we can take results of generative design and analyze them. What you see on the screen is mesh body that I brought into solid edge from STL file. We're going to be analyzing this bracket. The trick here is to have at least one analytical face. Then you will be able to use this body as a source for study. What we're going to do, we're going to add mounting holes. And the way we're going to do it, we're going to base off reference plane. You can see how easily we can add those holes to mesh body, and we can even use alignments like we normally do for placing these holes. This is really great approach to adding analytical surface. And finally, we're going to add additional mounting hole right here. For that, I'm going to show you the plane that I created, and we're going to use that plane to place additional hole. As you know, solid edge provides really great interface, and it ensures that users adhere to standards, whether it's ANSI, ISO, or any kind of industry standard. We're going to just place mounting hole here. And we're pretty much done. If you go into unshaded mode, you can see it's still a mesh body. So now we can go and start the new study. And because we're analyzing single part, it automatically accepts it as a geometry. All we have to do is just go and change the material. So maybe we're talking about aluminum 1350. What's left to do, of course, define constraint. And conveniently, we can use feature. Select all those 4 holes. That's another nice trick for productivity. Instead of trying to select hole by hole, you can select feature and select from a feature navigator. And as far as loads, we're gonna add load to this face, maybe like 100 pounds of force. And we're pretty much done. Now we're gonna be able to mesh and solve in one single operation. And again, as I mentioned earlier, what happens at this point, it takes all the boundary conditions, loads, and it takes them into an XNest behind the scene, and then the results are going to be brought back into post-processing window in the solid edge simulation. And that post-processing window or environment will allow you to interrogate the model and see how it behaves under stress and evaluate stresses, displacement, and all this data. So you can see we successfully analyzed mesh body. So as I mentioned earlier, this is a great way to analyze this type of geometry, whether it came from outside or a result of generative design inside of solid edge. And again, the trick here is to have at least one analytical body as a result of applied feature, and then you'll be able to analyze such part. Let's take a look at the tips and tricks when it comes to cleaning up geometry and being able to set up, study, and quickly analyze body when there are problems with geometry. So we have this part, and a couple of things I'd like to mention here. The first of all is you can see that we have the situation right here, which is usually not very good for analysis, where we have a little face that doesn't come exactly to the edge of the angle face. So this sliver situation right here, it's not really good for analysis. But for now, let's go and try to analyze it anyway. I'm not going to go through the whole analysis, just to give you an idea. We're going to focus on the mesh. So let's go into simulation and create new study. We're going to go after regular linear static tetrahedral. When it comes to mesh, when I try to mesh this, no matter what I do, how I adjust the slider for subjective mesh size, you can see that it's not meshed correctly. Even if I go with a higher number, usually it helps, but not in this case. Even if I go with a higher value, so let's suggest running geometry inspector. So let's do that. If I go and try to run geometry inspector, sure enough, I'll find two small faces. And that's right here. This usually happens as a result of imperfections if you bring geometry from other systems, or they translate it as IGES or STEP or any other type of translation. And solid edge usually is very good at not letting users create this type of geometry. But when it comes from outside world, in a lot of cases, or in some cases, I should say, it comes with this problematic geometry. But if I go and check this new option, which is called body mesh, and try to mesh it now, it just glides over it like there is no problem. You'll see how in a couple seconds it will come back and it will actually mesh over that that particular face, no problem. So this is great tip. If you're having problem with the geometry and it gives you some indication that geometry is far from perfect, you can always try this body mesh, and it will successfully mesh your part. Now, another area that I mentioned is this area where there is a little sliver-like part of portion of the top face, looks like sliver against that angle face. So for that, we have a different tool. But these two tools don't work together. So you can either use one or another one. The tip here is to fix your geometry before you use the other option. So we already looked at the body mesh option. Now what we're going to do, instead we're going to replace face. We're going to fix that small face. We're going to replace with that top face. And if I go and mesh it again, I don't have to check this body mesh. Let's go slightly coarser mesh. So when I mesh it now, if I go and look at this situation right here, you can see that this is not the mesh that ideal for analysis. And the reason being is that size of these mesh elements is much different from the size and the shape of other elements. So usually it's not a good idea to have analysis with this type of mesh. But if I go and check this option, under options, we have ability to say prepare geometry for meshing, and you can adjust this tolerance as you go. So when I mesh it now, you'll see that system conveniently meshes over that little face right here. And you get perfect mesh. All mesh elements are of equal size. So this is the perfect solution. So in this segment, I cover tips to use these both options depending on what problem you're facing. You can either use one or another if you're trying to fix geometry that came with imperfections from either as a result of design or came from outside world. In this example, we're going to take a look at another tip, how to display internal stresses inside of the part. So what we can see here is bolted couple plates. So let's go and take a look at the results. Another tip I would like to share with you is that now, even in a post-processing environment, you can still set planes and cut through your mesh bodies. And if we do that, you can see that right now, what we see here is only external stresses. There are no internal stresses displayed inside of the bolt, let's say. So let's go back. And what I can do, I can go and modify study. The trick here is to go into extended options and unselect this option, generate only surface results faster. So after this, when we solve this study again, you'll be able to see internal stresses inside of the bolt. It's very important because sometimes customers are asking for it. How can I see internal stress distribution inside of the body? So it might take a little bit longer because we uncheck that option for faster processing, but you'll be rewarded with internal stresses distribution. And it's important also to see distribution specifically in the hardware, such as bolts, pins, that kind of geometry. Now we have ability to observe internal stresses inside of the bolt. Another situation is when customers are asking to see only specific component, right? So for instance, if I go back and cancel this section in the post-processing environment, they want to see only bolt. So first of all, you need to hide all the components and check all the parts in the assembly tree. And then you can uncheck mesh bodies. So if I want to leave only bolt is available, I uncheck nut and both blocks, and you can see that we now have the hardware, the bolt displayed, and all the stresses are available. And if we turn on that section plane, now we can see internal stresses inside of the bolt. So this is a useful trick if customers in particular interested in internal stress distribution. Thank you for your time today. If you have any questions, don't hesitate to contact me. Here's my mobile phone and my email address. Thank you very much.